see. Can you see my slides?
Yes, sir. We can see.
Okay. Yeah, there's something block my screen. It say your default microphone has changed. I need to let this thing disappear. Hold on. Yeah, something blocked my screen. Yeah, there's something blocked my screen. Okay, I need to log off and log back in. Hold on. Okay, now it's okay now. It's working now. All right. Can you see my screen? It's a low pressure separation TA. Can you see the wording?
Yes, sir.
Okay. So we'll continue from yesterday. Yesterday we talked about the low pressure separation and the TA. TA means techno-economic analysis. Today we are going to continue techno-economic analysis, and then the focus today will be three sessions. We are going to talk about the CO2-free hydrogen production. We all know ammonia production. It doesn't matter green ammonia, blue ammonia. It's all about hydrogen, correct? So I want to refresh everyone's memory. If you look at this this diagram, so the half of this diagram, we are talking about the hydrogen production, all right? So I'm going to from here to here. So the orange circle, inside circle, these are hydrogen production. So today there will be two sessions talking about the hydrogen. What are the current way of production hydrogen and steam reforming? What about other way hydrogen production? So we already discussed about the electrolysis, green hydrogen using renewable power, but today will be the different type of hydrogen production. Okay, so then the hydrogen production, then the remaining here are the so-called the ammonia production, all right? In the ammonia production, the new technology we have discussed in the last 2 weeks. So we are talking about the low pressure microwave and also plasma, electrochemical, chemical looping. We discussed all kind of low pressure ammonia synthesis, and all this low pressure synthesis require new separation technology. All right. So yesterday we spent the 2 sessions and discussed about the thermal swing and then the cryogenic, all kind of things. I'm not going to repeat it. So then we come up with a techno-economic analysis, the so-called the whole plant system engineering approach. How much is it going to cost to produce the ammonia? Okay, so so that's what we left from yesterday. I hope you still remember what we discussed yesterday. So now let's continue. Okay. We also talk about the membrane reactor a different way. So again, so the low pressure TA is continue. TA stands for techno-economic analysis. And before you do the techno-economic analysis, you have to do the process simulation. Process simulation means you run the I-spin simulation. You decided the size of the vessel, size of reactor. We also practice how to calculate the size of reactor in chemical looping or in conventional. Remember, I have you do the exercise. What data in laboratory you need in order to do the calculation. Okay. So anyway, yesterday we showed the result. There are different cases, and then all the cases are related to the baseline. Haber-Bosch process, which is baseline. And then if you look at the case 1, case 4, case 1 is the microwave production, and then using the low pressure separation. Case 4 is the thermal swing ammonia separation, also using microwave. So the case 1 and case 4 both are the low pressure microwave followed by the low pressure separation. And compared to the baseline, which is Haber-Bosch, the saving are the utility cost, which is the operating cost. As for the AD means annual depreciation, which is capital, and doesn't cost saving because of the in base case the Haber-Bosch process is because economy of scale, the capital cost is very difficult to outperform compete with Haber-Bosch capital, but we can do a lot of saving in the operating cost. Why? Because of low pressure operation, and then we eliminate the high pressure compression and recycle. Okay, so this we've left yesterday. Any questions before we move forward to the next? Any questions? Great, go ahead. No question. All right. So anytime you do the more techno economic analysis, you need the data, all right? So yesterday we basically have a lot of assumptions here. So the total reactor volume, all these are the assumptions. Remember, I also show you the raw data from here. This is laboratory data. I mean, don't look at this data from the paper. The data looks a little ugly, but it's real data. But that's what you need. It's basically desorption time versus the so-called the solid solvent capacity. You can tell the shorter the better, right? The shorter time, the better the what do you call that, adsorption. So with this real data, we can basically plug in the data into the microwave and then do the calculation and then come up with this analysis, TEA. I want to just remind, I don't know if the audience, what's your background, either chemistry, chemical engineer, material science, or mechanical engineer. If you ever done the so-called process economic analysis or the techno-economic analysis, you need very good data. And if you don't have data, you can build a model. If you feed a model with the garbage data, and you will get a garbage result. So for the modeler, the famous slogan is garbage in, garbage out. So which means if you build a model, doesn't matter how good your model is. If you feed the unreliable data, it's called garbage data, you will get a garbage result. So what I'm saying that a good modeling work need a good experimental data. You have to be precise on experimental data. Otherwise, if you do not have a good either experimental data or good literature data, reliable data, do not do the modeling work because it's a waste of time. So it has to be reliable, the data. Okay. So anyway, so let's continue. We also have a breakdown cost, and then the case 1 and case 4 was the base case. And then this orange color, the base case, which is feedstock compression. Feedstock compression in Haber-Bosch, that's a big deal because it's a high pressure operation, and then you use a cryogenic high pressure cryogenic condenser, and then you have to recompress because when ammonia is separated, partial pressure drop, so you have to bring the pressure up in order to recycle. But low pressure, you don't have that problem. If you see the low pressure separation, the orange color, the feed compression is only 5% of overall cost. So which means the total cost is only 5%. And then in the Haber-Bosch is 45%. With case 4, also the low pressure separation thermal swing is only 5%. And then 2, there's the writer capital cost in terms of percentage, because it's new technology, small scale, and then the percentage of the total cost has the capital cost, which makes sense, all right? But Haber-Bosch economy scale, so-called writer cost is I would say probably 18% versus the 40% as a percentage. Okay. Any question before we move to other case? The next.
For the techno-economic analysis, for the scaling of the process, should we use any X factor? As you said, when we are scaling from 100 kg to 1 ton, like that, you are saying that X factor 0.6. Similarly, for techno-economic also, should we consider any X factor?
Yeah, I couldn't. Yeah, your microphone has a lot of echo. I cannot hear clearly. Could you repeat your question again, very slowly, because I cannot hear you, to be honest. Can you repeat the question again? Your question related to this slide, all right? So what's the question? Can you say it again? I cannot hear you.
Yes, sir. I will repeat the question, sir. Sir, when we are considering for scaling the process using our techno-economic analysis, for example, normal reactor, in a lab scale reactor, it will have a lesser cost and the factors will be minimum. So when we are going for scaling the process using the techno-economic analysis, should we consider the X factor, as you mentioned earlier, for example, the 100 kg to 1 ton or 1,000 ton?
No.
Like that.
Okay, that's good. Okay, very good question. Okay, so basically, all that's good question. So the Haber-Bosch the data so-called the baseline. Okay, you will see, and then in the new technology so very good question. For any economic analysis, you have to choose base case. So base case means it's more than likely base case is a commercial case. Okay, if you don't have commercial case, you have to run your own the laboratory data to create a base case. Okay, in this case, in Haber-Bosch, we do have commercial case. Two, the case 1, case 2 are in a laboratory, but we use the laboratory data to basically the measure the reasonable case. Okay, so very good question. Okay, let's go back to. Very good question. So you are talking about scale. I want to show you that I do have slides. I'm looking.
Slide number 18.
Hello, can you hear me? Yeah. So basically, we do have I do have a slide showing the scale. We are not analyzing laboratory scale. So we basically use laboratory data, microwave. And then we have we believe for microwave, what's a reasonable size that we are going to the plan. It's not going to be the Haber-Bosch 1,000 ton per day, but it's reasonable size. I'm going to it's 60,000 ton, but I want to look for the slide and make sure we okay. Here we go. You see the data. So all the cases we are talking about 6,000 ton per year ammonia plant. Okay, 6,000 ton per year ammonia plant. How much? It's a small scale because we believe for microwave or chemical looping, this is the size, so-called modular size we can build. But this is not laboratory. We use the laboratory data to basically project what's the data, productivity. Remember what's the size of reactor. The reactor, everything's a size based on laboratory data, but we are not the plant, so-called the microwave plant is based on this size, its production size. You follow me? So this size will be compared with Haber-Bosch 1,000, 2,000 ton per day. But we correct everything. If you look at the continue, wait for the next couple of slides. But we are not going. It is not apple to apple, just compare with plant size. But we basically compare on the minimum selling price, which means if you have Haber-Bosch the plant, what's the minimum selling price? Doesn't matter how big your plant is, but all go by the minimum selling price. For the smaller scale, which is the microwave the plant, what's the minimum selling price? That's comparison. You have to bring two different size of plant on the same basis. It's called the minimum selling price. Make sense? You will hear this in a next couple of slides. Okay. You understand what I'm saying?
Yes, sir.
Yeah. It's called minimum selling. Since you asked a question, I'm going to skip. I'm going to skip several slides and we'll come back. Okay. So maybe the very good question. You are asking question too early. So it's called MSP. Okay. See the MSP. MSP basically how do you calculate MSP? Minimum selling price. Okay. Minimum selling price means any production plant, if you produce ammonia, okay, how much you have to sell in order to break even. Okay, that means you do not lose money. So the formula calculation basically it's the capital cost, utility cost, raw material cost divided by price, and then also the heating value, and also the what you call it, and then how many hours you can operate a production hour. Typically, any the manufacturing plant, you have to consider the startup, shutdown, maintenance, and then you can operate 8,000 hours per year. So this minimum selling price. So we calculate using this formula, calculate Haber-Bosch the plant. We use this formula, calculate the microwave. So by using this formula, the size of the plant diminish. You follow me? The size of the plant diminish. That means I already give you credit of the Haber-Bosch plant. I already consider the size differences of microwave, but let's calculate on the same basis and we compare. You follow me? So MSP bring the Haber-Bosch and the new technology on the same basis. I think that's your question, all right? Okay, so let's go back. We will have a lot of data. So based on this, you'll see a lot of comparison, this yellow highlight. But I want to go back and then continue to talk. Very good question, okay? So basically this pie chart, and then disclose where are the savings of the new technology compared with the Haber-Bosch. The majority is the feedstock compression. All right, so there's no need to do the feedstock compression because we are dealing with the low pressure ammonia reactor, low pressure separation. So I have to go back, keep on going back and forth. These are three major vessels: cryogenic high pressure condenser, refrigeration compressor, and the recycle compressor at this period. And then as I mentioned, each compressor are three stage. It's not just one, it's three, because compress the gas, all the way to 250 bars. From low pressure, you have to have different stage. One compressor is not enough. You have different, so it costs a lot of money. And then the capital costs a lot of money, and operating cost is really utility, electricity cost. So all these are eliminated. Okay, the operating cost. All right, so let me talk about this. You don't have to read this wording. We presented, in many conference, and then you don't have to read the wording. I'm going to interpret this to you. Okay, so remember when you size the reactor, so you have a laboratory data, and then specific activity. That means per hour, per gram of the catalyst, how much ammonia you can produce. All right. So you use the data linear, we scale up. But in the real engineering world, you have to have the reaction kinetics. Actually, reaction kinetics means like something like this. You have laboratory data, you have to develop a kinetics curve in order to estimate the reactor size. So that means instead of coming out, this is the reason in the classroom I show you the specific activity. remember in the classroom we use this number laboratory data to the calculated reactor size. Remember that? So we have done exercise in chemical looping, and then it's very simple. All right, that's just one data point you calculate. Actually, in reality, you should use in the engineering world, you should use this formulation to the so-called kinetic rate, reaction rate, rather than specific velocity, because it's too linear, and you have to do the kinetics. It's a very complex process. Then you come up with this linear relationship. All these are so-called experimental data. You have so much experiment data, you come up with this linear regression. Other than just one data point from small, you project the large, but you have to do a lot of the kinetic study. Anyway, so this is in the real engineering world how you size the reactor, because you have to develop the rate equation. Okay, I don't want to go through here because go through detail, because if you are not in the modeling work, it's very difficult to interpret. But I want to tell you, scientifically or mathematically, you have to do reaction kinetics in order to come up with a parameter, the estimate. So you can see in this the equation, the Haber-Bosch, they already have the data in here. So then with the predictive model, we have some data. So you have to have the Haber-Bosch, the reaction rate, and also the new technology reaction rate. And based on that, then you can basically size the reactor kinetics. Okay, everything is based on kinetics in there. So it's very detailed work. So I have Dr. Devansu Bhattacharya have been doing this for so many years. Now, remember we have in low pressure separation, we talk about using the reactive adsorption, which is the magnesium chloride, and then actually that data obtained from University of Minnesota. And then this is the curve we use for the separation. How do you read this curve? This is basically partial pressure of ammonia versus the loading of ammonia on the solid solvent. Obviously, you can tell the higher the pressure, the higher the loading, all right? Remember yesterday we talked about the adsorption, desorption, thermal swing. The higher pressure and the more material you can adsorb on the solvent. Exactly, all right? And then this is the relationship between the four lines are the temperature. So the lower the temperature help the adsorption, which means at high temperature, higher pressure, low temperature favors adsorption. Okay, so all this data are from the University of Minnesota. Our collaborator, we use this, and in the simulation, you have to have a very reliable data. And as I mentioned at the beginning, if you do not have reliable data, it's essentially just your modeling work will be garbage in, garbage out. So you have to find reliable data. Now, even with the reliable data, we found we can only work in the low pressure range. If you look at the low pressure range, which is about 1.5 bar ammonia partial pressure, because this is the experimental data, we have to basically extend it, which means extrapolate, because in the laboratory, they can only measure, the ambient pressure or the little bit lower than ambient pressure. But what if we need 1.5 bar? So we have to basically fit this data with some curve. And then true, we don't want to use very far the projection, because it may not be project very well. So we kind of put a square shape the data, saying, hey, any data, project data within the 1.5 bar, probably we can utilize for our modeling work. So that means our downstream separation, the ammonia partial pressure cannot go very high, because if we go very high, and then they probably go out of range of this experimental data. So each curve they have like 3 data points, and then we had to extrapolate. Okay, so anyway, so that's how you get data. You have to either you have your own laboratory data, because our focus on microwave is based on the reaction. So we team up with University of Minnesota We basically saying, hey, you do separation, give us the reliable data, and we collaborate putting together in this the so-called plant-wide model. Okay. Anybody has any question about this the data and how we put the data in how we put the kinetic data, which is related to reactor reaction and reactor size, and also productivity, and also the temperature swing adsorption data into downstream separation and roll into the equation. Anybody have any question? No, no question. Yeah, I think since this recorded line, you can see I give you the paper here. You can basically follow paper. We publish a lot of paper, in this field, and also and also the University of Minnesota also publish a lot of data. You see my collaborator here. Yeah, it's basically a professor of McCormick. He published in paper in ACS Sustainable Chemistry and Engineering, and that is curve. Okay. Anyway, so with all this data, reliable data, we put in the model. Now come to your question. You mentioned about Haber-Bosch plant is the large, and then you have laboratory data, and then how you compare. Well, we use our laboratory data to make projection, and then hey, we use our laboratory data develop kinetics, and also using again laboratory data, and then to size the plant at 60,000 tons per year, which is not the size of a Haber-Bosch plant. Remember, Haber-Bosch plant is 1,000 tons per day, but we are 60,000. What is 60,000 tons per year? It's just like probably a small scale compared to Haber-Bosch. But we correct everything, calculated based on MSP, minimum selling price, and to compare. In here, we have to make an assumption of raw material cost. This RM means raw material cost. Raw material cost means hydrogen, so it's about $2.07 per kg in the United States. And then nitrogen, you do need to pay the nitrogen price. Nitrogen is more like this in your economic analysis. Either you buy nitrogen from somewhere, or you build the so-called the air separation, but you don't have to pay nitrogen, but you have to pay capital. Follow me? So let me just show you. I want to make sense when you do the engineering economic analysis. I want to show you what is the practice of what is the practice when you determine how you build the capital and operating costs. Okay, let me know. So this square is so basically this square shape is the boundary of your plant. Okay, so let's see the nitrogen hydrogen. So remember, you have in the real world. In the real world, the hydrogen is in your boundary. All right, you have to your ammonia plant has to have hydrogen production unit, and then in your what do you call that? In your boundary, you have to have the air separation. But in the modern modern ammonia plant operation, your because air separation actually very expensive. You may not need the air separation. Okay, air separation unit. So there's a trick you can play. I used to teach. I teach the refining the chemistry and process and also economics. So I will tell students, so you have to when you build the plant, you can't build everything. You have to consider what other people can help you. I'm talking about the strategy of the obtaining nitrogen. Here you can see we have to pay the price of the nitrogen. It's the air separation. So there are two ways you can handle this. Okay. So one way handle this is called ASU. Oh, geez. ASU means air separation unit. Okay. So if you build ASU inside the boundary of your plant, you pay the capital cost. Okay. So if you have this, you pay. If you do this, you pay capital cost. Okay. So that means here it's going to be 0. Okay. So it's not going to be it's not going to be 0.04. Here's going to be 0 cost because you already paid capital on it. Now you can do the different way and then build this outside your fence. So then you pay the 4 cents per kg. So you may be wondering, who is going to build outside my fence? Well, I do not know how the business is operated in India. Okay, so in US, everything's private. Okay, all the company you name is private. There's only one government-owned company. I don't know if you know that in US everything's private. There's only one government-owned company. It's what? US Postal Service. Postal Service is government-owned. In the US, everything's private. So you can talk to a company, ASU, saying, "Hey, you build this outside my fence," and then the company will say, "What's the benefit?" Well, the benefit will be you give me this nitrogen, and then I basically I will have a contract with you for 20 years, and then pay you 4 cents per kg for 20 years. So this company calculate, oh, if I have guaranteed a 20-year purchase, and then selling like 4 cents per kg nitrogen, I'm going to make money. So then they're going to put capital. This is going to release your burden. So that means you do not need to have this in your plan. Make sense? Do you understand? So that's why I'm trying to give you a very good example how you see this a calculation. This is your capital cost. So this is your capital cost, and then this is your operating cost. Okay, so you really have to balance your capital cost and you basically operating cost. Here, if you build the ASU inside, you pay AD, and then if you move it outside, you don't pay AD, but you pay the utility cost. So you have to balance the strategy, but you are not going to save money. That means at the beginning, if you don't have a lot of money, you have other people build it. So you slowly in 20 years, you pay operating costs. That's one strategy. It's more like you buy a house, right? I don't know in India. In India, if you buy the house, you pay the mortgage. And in US, the same thing. So I mean, slowly I pay you. I don't have a big chunk of money, but I'm going to let you lend me the money. Okay. All right, I'm going to move on. Anybody have any question here? No question? Okay. So under this equation, the interpretation is here. Basically, the ADUC raw material, these are costs, and then PC basic plant capacity times the LHV. Anybody knows LHV? LHV stands for? In engineering world, you should know LHV. What's the LHV?
Lowest heating value.
Thank you. Yes. So basically, you have to divide by the plant capacity, which means is it going to be the 1,000 ton per day or the 2,000 ton per day? That's the so-called PC times the low heating value of the ammonia times 8,000 hours. Okay, so altogether that come up with the MSP. Okay, so now I'm going to flip to the next one, And then what's the result of different cases? So this is the result, okay? So let me see the, okay, I'm gonna circle this. Here's the result. Yeah, I hope you understand engineering economics. It's very important. I can tell you, I work for the two large company in US. One is BP, which is British Petroleum, which is I think is a very large the oil company in the world. The other is called the Coke industry, which is the largest private company in US, working in the refinery. So if you go to any industry company, true, you do have technical people like you guys, like PhDs, but there are a lot of the so-called analysts. They do this the economic analysis every day. So anything before you even run experiment and all the invest the so-called R&D money, you have to run all the economics and see if it makes sense. If the economic doesn't make sense, nobody put the money, nobody invests money even in the research. Okay, so the industry doing different. In the university, we do research because we are talking about next generation technology. That's government supposed to pay. But industry all about the money. They do TA first before they even invest in there. So the TA is very important. But a lot of the I would say the researcher undermine the TA. But I would anyway. So see you understand MSP, all right? We put all these cases with the basic cases together, and then look at to look at the MSP. So typically the rule of thumb, the base case for the ammonia synthesis, the base case is about 11 to 13 cents per unit of the ammonia. Okay, so let me interpret this. See my yellow highlight? MSP dollar per kilowatt hour. This kilowatt hour is now electricity. This kilowatt hour means it's a heating value. Okay, it's heating value. So basically, the kilowatt hour is a heating value. So that means to produce 1 kilowatt hour heating value of ammonia, how much is it going to cost? Okay, so to give you another example, it's a heating value. It's not electricity. It's basically it's ammonia. I would say it's a per unit of ammonia. Okay, so how do you understand the kilowatt hour? Okay, 1 kg ammonia LHB equals 5.6 kWh. Makes sense now, is that right? So basically, 1 kilogram of the ammonia, the heating value is about 5.6. Okay, so that means 1 unit of the 1 kilowatt hour of ammonia. If you want to turn this into the weight of ammonia, it's going to be 1 divided 5.6, okay, kg. To say different way, to produce 1 over 5.6 kg of the ammonia, and then how much dollars it cost for all the cases. Now you see we put a different case, case 1, case 2, case 3, and case 4 all together on the same basis, and then compare with Haber-Bosch. So Haber-Bosch 11 cents. You see all those cases. Some cases make money, which is less than 11 cents. Some cases are expensive. So like a case 3A, case 3B, they are expensive because they're obviously the vacuum TSA and vacuum TSA is not as good as the membrane. It's not as good as the cryogenic flash separation. Okay, so the cases 1 to 4 we put together, they are not all make money compared to Haber-Bosch. It's all depend on downstream separation. So some cases like 3A and 3B, they don't make money at all because they are more expensive than the Haber-Bosch. So what does it mean? That means you just don't build the plant like this. Remember, I tell you in industry, we do when I work in the industry, we do this all the time. You have to run the economic, the see makes sense. That means in this case, we even don't bother to do the experiment in this the field. Okay, they say okay, don't even connect the vacuum TSA with your ammonia. Look for something else. I mean, let's do the case 2 and case 4. So that's R&D, research and development investment. You're supposed to go into it. Okay. Anybody any question at this point? Yeah, this is very important because TA analysis is not just like after fact interpretation. This in the most of the industrial process, they use this even before you do anything, before you do R&D or before you build a plant. Some of the technology you do not need a research and development because it's already there. But even that, before you build it, you have to go through all this technical economic analysis and then to make sure you make money before you even invest. Okay. Understand? Any question? Okay. No question? All right. So let's continue. So based on the, this is basic interpretation on the why the 3A, 3B doesn't make money. And then cause I don't want to spend too much time. Only when you are interested, I can show you all the paper. We publish a lot of paper in ammonia. And those papers led by the Dr. Devanshu Bhattacharya. Dr. Bhattacharya and I, we work together. So basically, I'm in charge of all the entire project on the reactor scale up, but he does all the economic analysis and then also the marketing. Okay. All right. So let's keep on going. All right. Technical economic analysis and the fight. Okay. Let me see. I want to show you. Okay. So let me tell. So this is basically the technical economic analysis. You use your experimental data, or I would say, or literature data. Like in our case, we have experiment data on microwave. Then we team up with the University of Minnesota, get downstream, put it together. So the table here shows what you call that. I would say preliminary TA, technical economic. Preliminary means it's not optimized yet. So based on the data, we have to sit back and do all the analysis. Okay, so can we optimize it? Yes, of course you can optimize because you have to see where are the money wasted. Okay, so you do all this to the TA analysis, look for maybe we change the pressure or change the downstream separation approach, and then overall we want to reduce the MSP. Reduce MSP means we can sell at a very low price, still make money. Okay, so that's called optimization result. So you do all the optimization by improving it, and then you want to see what is going on. So after the optimization, we found case 1, case 2 can further going down, MSP can further going down to less than 10 cents. Okay, so if you are interested, I can tell you what optimization we are doing. But this more like I would say the paper study, which means what if we, the change this process here, change it there. So we come up with this. So I'm gonna go back. Case 1 become $0.09 dollar per unit ammonia, and then case 2 become 0.105. What about the previous data before optimization? Before optimization, case 1 is the 0.101, and then case 2 is 0.108. We do have improvement. And by the way, this number, this is the meaning, okay? The 3 digits after decimal, yes, they are accurate until this one, because when we do the simulation, we do have 3 significant number after decimal point. It's very precise, the calculation. It's not just random. We keep a 3 digit after decimal point. You see the case 1, case 2 has been further improved, and then the lower. So this is how you do the technical economic analysis. You come up with the preliminary data, you optimize, and then you do optimization again. After you are done this several cycles, and then you optimize your plan. Then that's the time you select technology, you select R&D or research development investment. Make sense, everyone?
Yes, sir.
Okay. So, I mean, we can further talk about how we optimize this, but I don't want to spend too much time on this because it's just too much mathematical. I know the audience, if you are not in economic analysis, you will be really getting bored. So there are a lot of detailed optimization we have done to optimize design variables for case 1, case 2, because we know case 1, case 2 is the way to go. Okay, so let me summarize the so-called this is our future work. And I would say today we already reached the in the Haber-Bosch the plant laboratory, we already reached this scale, kilogram per day scale, and then at the single pass conversion 9.6. Remember I asked you to calculate the conversion, single pass conversion. You know, if you measure the ammonia concentration, what is single pass conversion of nitrogen or hydrogen? So, and then I think at that time the answer is, I think it's 9.5 something. So that's actually based on our real data I give to you. So purposely, I didn't show you the conversion, but I show you the ammonia concentration at the back end. I think remember the case study we did, 9.6 single pass conversion. This is very significant. The reason being that if one reactor single pass conversion is this much, you can have 3 reactors and achieve very high. So that's normally the Haber-Bosch plant has been built. But in our ammonia plant, we can build the same thing. So 9.6% conversion single pass, we continue until the certain conversion level, we can do the recycle. So this is, and I think about we are speaking this technology, microwave, we already reached the kilogram level. We are building like a ton level, so 1 to 2 tons per day. So 1 to 2 tons per day ammonia already considered as small scale production because the farmers need that small scale. But if you have a Haber-Bosch plant build 1,000 tons per day, you need a distributor to distribute this to many farmers. But for the renewable power, if you have the small scale, you can sell to the local farmers. Okay, make sense?
Yes, sir.
All right. So this is status. So what's the next? Next, we can build the large scale single pass conversion, 90%. But that's in the technology future. But all of this, you see, if you see our technical economic analysis, we have very good data to back it up. Okay, so now with the technical economic analysis, we actually further project. So we can, if you have our reactor up to 5,000 psi and cases, our single pass can reach this much. So economics will be doing even better. Okay. All right, so that's the pretty much what we are doing on the TEA. Before I shift to the next section, I'm going back to today's topic. So I think we spend quite a bit of time on the TEA. Well, we lectured low pressure separation, and low pressure separation, that's 4 different cases. The low pressure separation can be tied with low pressure microwave. All right, that's how you come up with a TEA analysis, and you can tell with the microwave ammonia synthesis and also the low pressure separation, we can outperform a Haber-Bosch. I mean, which means the technology will achieve better economics than Haber-Bosch. That's what you want. All right? Otherwise, if you don't produce the ammonia comparable with the Haber-Bosch, I mean, nobody care about your technology. So you have to be really careful. So I think the next 2 sessions today, we are going about the CO2-free hydrogen production. Okay, so remember, ammonia production is all about hydrogen. Doesn't matter you start from coal, you start from the biomass, start from natural gas, you have to produce hydrogen. Even with the renewable power, you have to do electrolysis. So you feed out with water, but you will spend a lot of renewable power to generate hydrogen. So all this process, only thing when you say green ammonia or green hydrogen, you do not want CO2 produced, all right? So that's why I'm going to show you the CO2 free hydrogen. I'm sure you know blue hydrogen. I'm not talking about blue hydrogen. I'm going to talk about different color of hydrogen. Okay. So, all right. I will save the time. I think that's still probably the 6 or 7 minutes left. Maybe I think it's the lunch time now, right? I will have you guys to go for lunch, and then I will put up my slides. And then when you come back from lunch, I think you have 1 hour break from lunch. When you come back from lunch, and let's talk about another way to produce a so-called clean hydrogen or CO2, the free hydrogen. Okay, will that be good, everyone? Okay, see you 1 hour after lunch. So today will be all the hydrogen production. So you will like it. Yeah. Okay.
Thank you for your
see you 1 hour.
Thank you.